Morning, guys. I bought this cheap LCD shield for the Arduino. It's also got a touch screen attached to it, and I got this from Banggood for under $7. There are some drivers that you can download on the Banggood site, and there are a couple of videos here that were helpful in getting this one on the right. Was particularly helpful for getting everything going. So it plugged into my Uno, and I managed to do the little things and use the touch pen and so on and so forth. But it is slow. It and in the one download for the driver, they've got some sample code, and the very first sample avoids all the imported libraries. It doesn't use Adafruit libraries or anything, and what they do is they just directly bit bang, or they turn the bits on and off to clear the screen and put different colors onto the screen. And that's the example I worked with. And my objective was to now move this device off the Arduino onto the ESP32, and then play a little game and try and see what's the highest possible rate at which I can move data from the ESP32 onto the device. And I'll give you a teaser up ahead. I managed to get extremely good rates. I surprised myself. So in excess of 30 frames per second, and that's a full 320, 240, and each 16-bit. So we're looking at a data rate of more than 6 megabytes per second to sustain that. So I'm going to show you how I did that. So let's begin with the Arduino code, not the ESP32 code. If we look at this example, I could get about, it took about 3 seconds to clear a screen to a background color. So if I wanted the whole screen transmitted to make it blue or red or green, it was taking about 3 seconds. And the heart of the algorithm is where you actually write the data out. And that 3 seconds was the optimized version for the Arduino. What happens is, instead of using digital read or digital write to set a signal line high or low, what you can do on the Arduino is you have a number of ports, and you can just write directly into the port. You can put your ones and your zeros in the ports to change the bits, and that's considerably faster than the library routine to do a digital write. So that's what the original author of the code did over here. We've got 8 data bits that we've got to move around. 6 of them are wired into the Arduino into port D. And so when you want to write some information into the port, you kind of strip off those 6 bits of the information, and you OR it into the information that is already in the port. And the other 2 bits you put into the other port. And then in the way the LCD works is, when the clock pulse goes high, this is the clock, a thing called LCD write pulse, which in this particular case is was wired up to line A1, the analog 1 line on the Arduino shield. When this line goes high, the data gets moved across from the pins and gets latched into the LCD screen. And then you make the right line low again. So you've got to pulse the right line. So this is what he did there. Now, the problem with this code is that it's not portable. I can't take this code, or when I try to compile this code on the ESP32 architecture, it said, no, we don't have a port D, we don't have a port B, you can't work like this on this architecture. So you can substitute, you can undo these optimizations and change this thing back into digital write LCD, put the pin high, and then digital write over here and put the pin low, and you can get rid of these two lines, and that'll work on the ESP32. And over here you need 8 bits. You want to set some digital lines, so you need a little bit more work. You have a loop and you unpack the bits out of the byte and you work out which line you want to set, and you either set it high or you set it low. So I put those changes in this code. That slowed down instead of me getting 1 frame every 3 seconds, I now got 1 frame every 5 seconds on the Arduino. But the code became portable, so there wasn't too much to change. There were a couple of lines here, a couple of lines here, and then after that everything was reasonably abstracted away, and it would work on the Arduino. I put some timing into the thing as well, just to give myself an indication of how fast things were going. So what I do is I clear the screen, and I take the time beforehand and I take the time afterwards, and then I can subtract the 2 times, and it'll give me the number of microseconds needed to write the 320 by 240 by 2 bytes each color into the screen. This is an RGB 565 representation, so the first 5 bits are your red channel, the next 6 bits are the green channel, and the next 5 bits or the blue channel. And so every pixel that you write on the 320 by 240 needs 2 bytes. And once you've done that, he had some code in the original example. Not all this code worked out of the box. I had to do some fiddles before it got it to work, but I've got a little thing here to draw 100 random rectangles, and you put each one at a random X, Y, width and height, and you give it a random color. And and then you print out the timings. And so I was getting about 1 frame every 5 seconds. When I ran the code the first time on the ESP32, it was considerably better. I was getting about 3 frames per second. So it looked like the code was probably almost 10 or 15 times faster. It wasn't nearly what I wanted, though. I wanted to get up a lot higher than 3 frames per second, and as I mentioned earlier, I surprised myself. I'd set a target 25 frames a second, but I'm currently running well above 30, so we'll have a look at that. So here's some of the ESP32 code, and I'll try and explain what I've done here. First of all, I took the data pins, and I've got the least significant one on this side. I used pin 12 on the ESP, and pin 13 is the next significant bit, and then D7, the most significant data bit, was wired up to pin 14. So I took my wiring and I stuck it in place there. This line can go. And then I put I chose some other pins for the 5 control pins that you need. We don't use all 5. We don't reset this thing explicitly, but it was in the code and I left it there. Now, when you just, as I said previously, when I just use digital write high, digital write low, then what you need to do is you need to take your byte and you need to unpack it, and you pick the bits out one at a time, and then you decide whether to write the corresponding line high or low. I put all the pin numbers in an array over here, so when I get the least significant bit, I set pin 12, and the next significant bit I set pin 13, and the next significant bit I set 23. So I need a little loop that runs around 8 times to do that for me. I didn't eventually do it that way. That was one of the bottlenecks, and that's why out of the box I only was able to get about 3 frames per second. Now, how can you speed that up? We want an equivalent of what they have on the Arduino, which is to be able to directly write to the ports rather than use a digital write or digital read. And one of the reasons for that is, if you want to understand the reason for that, we need to look at the code for digital write and digital read and see if we can make any sense of it. So Yes, out of the ESP32 library, this is actually the code that gets executed when you call digital write. Now, the ESP32 is a 32-bit architecture as opposed to the 8-bit architecture of the Arduino. So the I/O ports, the GPIO ports exist like they did on the Arduino, but each one is 32 bits long. And so, and there are two, if you know your ESP well, you'll know that you're allowed to write to any of the pins up to about pin number 33 is the last pin you can write to. After that, they are read-only pins. So if you look at this code, the way it works is you say, I want to write a high value to pin number 27. Starts off and says, if you want to write a high value and your pin number falls within the first port range, then you're going to kind of shift a 1 bit along into the correct position to make a mask, and you're going to jam it into the GPIO register. And if your pin is number 33 or 32 or 33, then you've got to write to a different register. And if you're trying to write a 0, you have to do something else again. So there's quite a lot of work you've got to do to write a single line high or low. The interesting thing about the ESP32 is they have these two registers called write1 to set. So it looks W1TS and write1 to clear. And essentially the nice thing about this architecture is you don't have to read the port to know what the other pins are. You simply set their bits to 0 and you put ones where you want the bit 1 to be written. So write1 to set, you put a 1 in, or you put multiple ones in the correct positions in the mask, and then you write them all into the register, and all those pins get set and none of the others get changed. If you want to clear the pins though, you've got to write into a different, you've got to put ones again in your mask, and you've got to write to the clear register, write1 to clear, and those pins will then become 0. So this is what we're going to exploit in our code. We're going to try and figure out how to do this. When I want to write 8 bits of data to the LCD, I'm going to set up 2 masks with ones in the correct places. I'm going to put ones, and the correct places will be according to my wiring diagram, which pins are wired to which data lines. Those will be the correct places. And then I'm going to work out which bits need to be a 1, and I'm going to make a mask, and I'm going to jam it into the write1 to set register. And then I'm going to work out which bits need to be 0s, and I'm going to put 1s in that mask, and I'm going to write it into this place. So that's how we're going to get the equivalent of what we had on the Arduino. We're going to fiddle with the GPIO ports. But, of course, working out which bits need to be written. If I'm trying to write the value 23 and I convert it to binary and it's a 16 and it's 16421, I need those bits set. Then what I've got to do is I've got to, in the one mask, I've got to put the 4 bits on, and in the other mask I've got to put the other 4 bits on, and they've got to be in the positions where the wires are connected. And then I can write, with 2 writes, I can set the bits I need to set to 0. I can set the bits I need to set to 1 over here, and I can set the bits I need to set to 0 by writing into the other mask. So that's the way we're going to try and do it. Okay, so let's go back to the example I used. If I've got the value 23, and I convert it into bits, it's going to be, the binary representation is going to look like this. It's going to be 1, 2, 4, 8, 16. It's going to be a 16, and a 4 is 20, and another 2, and a 1. So that's my binary for 23. Now, what this means is if I want to transmit that 23 to the LCD, I've got to set pin 14 to 0, pin 27 to 0, pin 26 to 0, pin 25 to a 1, pin 22 to a 0, pin 23 to a 1, 13 to a 1, and 12 to a 1. And what I can do is I can do that with 2 masks. Now the masks each have to be 32 bits long because they're 32 pins, but I can set the mask up so that it has a 1 in position 12, 13, 23, 25, and I can write that into the register, where if you write those 1 bits, it'll set the bits. And then for pins 22, 26, 27, 14, I put 1s in the mask in those positions, and then I'll write it into the register that'll force the bits to clear. So in 2 writes, I can set these 4 1 bits, and I can set these 4 0 bits. So that's what I want to do. I want to have these masks and be able to put them there. Now, the most interesting thing that I did here, the kind of key thing to make it go fast, was that I can pre-compute those masks. There are only 256 different possible values that I'm going to want to write. A byte's got one of 256 possible values. So any byte that you give me, I can pre-compute what the mask needs to look like, for which bits need to get set and which bits need to get changed to 0. And so I declared 2 arrays here, the output set map and the output clear map, and each one of those arrays has got 256 elements in it. And before I go into the computation, what I do is I populate these 2 maps that I've got with the corresponding mask values. Now we're on a ESP32. We've got a considerable amount of memory, more than we had on the Arduino. So having a 256-bit array and a 256-bit array is not a train smash. We can do that quite nicely, and we've got memory to do that. Once I've got that map set up, then if I'm trying to write a 23 to the port, all I need to do is look up the mask here and jam it into the set register, and then look up the mask here and jam it into the clear register. And so here's the code, the critical code that does the hard work for me. When I want to write a byte D, I'll look up what its mask is, and I write it into the 1 to set register. When I then go and look up which pins need to be low, and I write it into the register. And now what's required is to toggle the right line, to strobe the lines so that the LCD screen latches my data, and it latches the data when the pin goes high. And so what I do is I set the pin high corresponding to that strobe line. You'll notice that I stuck the mask out ahead here. That particular right line's on pin 18, and so in the 18th position I put a 1 bit of this mask, and that means in an array lookup, change the pins, another array lookup, change the pins that need to be low, and one more write to push the right line high. You may be wondering where the right line went low again. It's when this code started off, I had 2 instructions here. I set the line high, and then I had to bring it down low again. But it turns out that you can optimize even further. You can say part of your output clear map, always clear this mask bit as well. So while I'm writing my 0 bits for the data, I also write the 0-bit for the mask line to go down. So in these three three moves over here, I've managed to write out 8 bits at a time. And after that, it's quite there's not a lot of logic in what I'm doing. If I want to write a command, I set the appropriate bit. Where has my cursor gone? Over here. If I want to write a command, I set the line for the command low, and then I write the data out. If I want to write data, I set the line high, I write out the data, and then the rest of the code is as it was on the Arduino. When I want to, if I've got a region where I want to put the data, I identify that region to the microprocessor that's on the display, and I say I want to here's a command coming. I want to set a region, and I set the region, and then the data bits that follow that will actually get pasted onto the right place on the display. So now at the end of all of that, I can come down here and sort of say I've left all this other code intact. It's more or less what came, and now all I've done here is I've said, let's look at the background colors. That's going to be red, that's going to be green, that's going to be blue. I've got a loop counter. I decide what color I want the background to be. I get my timing to happen, and I clear the background color, and I get my timing to happen again. And I'm interested in how long it took me to send those 256 times, or not 256, 320 times 240 times 2 bytes each. And so this T1, T0 is the important thing here. Once I've got that, I can work out how much, that's how many microseconds it took to set all the pixels. That will give me a frame rate, and that will give me a data rate. And lo and behold, if we open up a serial monitor on this and look at what's happening, if I can find my serial monitor, tools, serial monitor. Ah, there it is. Right. This thing is now reporting that it's taking 23 milliseconds, or 23,000 microseconds if you prefer, to set all the screen pixels, and that corresponds to a rate of above 42 frames per second. And when you do the little sums about saying how much data am I actually moving out here, I'm moving out more than 6 megabytes per second. So that's a pretty impressive result, I think. 6 megabytes, each one of them 8 bits long. That's I'm around 48 or 50 megabits per second that I'm managing to push with fairly ordinary code, not a lot of it, out of the ESP32 onto the screen. I will post this code online. It's not useful yet. All it does is clear the screen and draw some little rectangles. But I will look at whether I can capture frames from a little camera, an OV7670 camera, and see whether I can capture them at this resolution and at this rate. And while I'm capturing, try and move the data onto the display. So thanks for watching, and I'll put a little URL where you can download this code and try it for yourself.